Hey everybody. Yeah, so I'm going to talk about the near-infrared volatile spectrometer system, and specifically kind of how the systems, the particular system that's flying on the Astrobotic 1 mission in July of 21, along with a number of other instruments you heard about here today. The near-infrared spectrometer system is a system of sensors. It's not just a near-infrared spectrometer. It's led by myself here at NASA Ames with a close partnership with the Brimrose Corporation on the East Coast. We got connected with them through an SBIR, actually, and I think this is a great example of how SBIRs can really bring a lot of, or how valuable they can be and how effective they can be in terms of developing instrumentation for flight, actually going forward. It's got four components to it. It's got an AOTF, acoustic optical tunable filter near-infrared point spectrometer that operates from 1200 to 4000 nanometers. And it has what we call a spectrometer context imager. It's a 4 megapixel imager. It's a CMOS imager that uses then LEDs between 340 and 940 nanometers to image at multiple colors. At about 1 meter off the surface, its spatial resolution is about 1/4 millimeter per pixel. It has a long wave calibration sensor, and this was added. Originally, we ran out to about 3400 nanometers. We knew just based on the MQ'd experience how important it is to get that thermal correction right. So we added this set of sensors to be a calibration sensor. Now that we're out to 4000 nanometers, it's not as important, but it's obviously an important contextual measurement as it provides surface temperature of the area we're looking at. And lastly, we have a lamp. So this instrument's meant to work in day and night and PSRs and dark places. So we brought along a lamp as well. It's a dual filament tungsten lamp, very simple, but it provides a very even, well-calibrated light source for the near-infrared spectrometer when we're in shadow. And there's a number of specifications there on the right-hand side. It's TRL6, will be 9 when it has an 8 Astrobotic in about a year or so. And it's a little bit, about 3.5 kilograms and relatively low power. The lamp is a big part of it at 12 watts. The key measurements are, of course, to look for volatiles, hence the name volatile spectrometer. And so a lot of the wavelength coverage was selected specifically to do that. The upper right-hand corner shows a graphic of the wavelength ranges that we cover and some groupings of particularly strong ice and mineral organic absorption bands that we'll be sensitive to. The spectrometer has two channels of what we call a short wave and a long wave channel. That's what's shortened by these two lines here, the blue and the red curve. And these dock LEDs, that's the camera LEDs, are shown here as these stars. So we cover quite a large range of various both ice volatile features, but as well as mineral features. Also down here that shows, just for reference, some examples of the types of minerals we'll be sensitive to, as well as with the spectrometer, but also with the LEDs. Each of these bands here in this lower figure shows the LED positions in our camera. Last thing I would say here is we will be able to measure temperatures down below 100 Kelvin and up to about 380, 400 Kelvin as well. This shows the working end of the instrument, if you will. It shows a basic close-up of all the various sensors and lamps. Here's the IR lamp. It's got a cut-on filter on it, so we can operate the lamp at the same time it's doing imagery, and they won't interfere with each other. This is a spectrometer fiber viewing aperture. It's a 38 fiber bundle that looks at this lens aperture and feeds into the two channels of the spectrometer. This is the 4-channel thermal radiometer. It's a 10, 14, 25, and a broadband, basically 6 to about 30 micron filter set. Allows us to get temperatures very accurately. It's all thermally stabilized to less than a degree centigrade, so we can get really nice measure temperature. And then these are all the various LEDs that work to help illuminate the scene for the context spectrometer. Each color has approximately 3 LEDs, and they're put in bundles like this to help with shading effects from the LEDs. This is a spectrometer. It's, I mentioned it's a dual channel spectrometer with 2 fibers. It's fiber fed. The fiber bundles split and go into each of the 2 channels. Yeah, that's all I need to say about that, I guess. It's what's nice. It's an AOTF spectrometer, so it's very programmable and tunable with no moving parts, and so we can dial in the resolution, the wavelength coverage we want, et cetera, and to really manage our bandwidth, our data bandwidth, for example, and increase signal and noise, et cetera. It's unfortunately not the greatest image that I grabbed here, so it's a little blurred. This is how it's being accommodated onto the astrobotic lander deck. It's hanging down from the deck, like you've seen in some of the other presentations. The cage is an adapter that goes around, holds the spectrometer here with the fiber that twists around and feeds into the spectrum, or into the what we call the bracket assembly, where all the sensors are. It's looking straight down from the deck at the surface. Really maximizes our signal to noise. Doing so, this whole thing will be wrapped in MLI then for the mission, except for the apertures, obviously. For the astrobotic mission, the quick summary of the CONOPS is shown here. We really do want to look at both sunlit and shadowed regions, and our particular, where we're mounted on deck B, it looks like we'll have an opportunity when you first land to see some shadow regions, which is great. And then as the day progresses, be able to watch as those shadows move out of our scene and get illuminated by the sun, and we'll then look well into the later day hours of the lunar day. We plan on operating for 45 minutes twice a day, and that gets us full scale 4 megapixel images at all colors and basically no color, so a blank, if you will, and also up to about 1,000 scans of the spectrometer. So we should have very, very high signal to noise spectra at that spot at any time. Temperatures run continuously. We basically get a temperature measurement every second. We're designed to work anywhere between this distance. That's really drives the focusing of the lenses that we use and whatnot. Right now, we're shooting for about 75 centimeters for the astrobotic mission. And then, it's the colder the better for the spectrometer, of course, since it's a near-infrared spectrometer. So we expect really good signal and noise very early on in the mission, which will be really interesting because that's when the surface will be coldest as well. Of course, we're looking for the hydration, with this instrument, and we're very interested in how that hydration changes as a function of lunar time of day. We're going to be, it's going to be really neat to be manifested with the other instruments who are also looking for hydration signatures, and at the end of the day, compare each other's results and see exactly what it is we saw. So it's going to be a really great opportunity to understand that. As others have mentioned, there will be propellant. It's lander, and as it comes down, it's spraying a considerable amount of water and other volatiles all over the surface. But just seeing how that changes over time, monitoring that is actually a very interesting active experiment, if you will. And maybe we can get a good handle on the volatile migration and sticking on the lunar surface, looking at these data as a function of time. We are manifested on the polar mission, and in an earlier meeting last month, we talked with a number of the other instruments going, and I'm looking forward to hopefully working with the sampler arm, being able to put samples in front of the field of view for NIRVSS in that mission as well. So that'll be really exciting. Where we're at right now, building up, we are currently building the flight instrument for the astrobotic mission. We started environmental acceptance testing in a couple weeks. This photo shows some of the various pieces and parts coming together. This is a foot set for the fiber bundle rigid assembly that goes into the bracket. Some of the fiber baffles and lens assemblies being built, spectrometer and acceptance testing. One of the things we did actually, again, just to optimize things in a somewhat different way than NASA usually works, is we're building two of these units in parallel. Basically, the first unit's going to be ready at end of April for astrobotic. And the second unit then, which is manifested on the CLIPS lander that's to go to the polar region, will be finished shortly behind it in May 2020. So it's just optimizing basically the people, facilities, and places, getting all that into one place at one time is a hard part. You know, when you buy parts, you get multiple pieces. So then it was just pretty straightforward to build two. And so that's about where we're at. I'll take questions if there are any.
Great. Thank you, Tony. There was one question so far in the chat. What is the noise equivalent delta temperature on the radiometer measurements at less than 100 K?
Less than 5 degrees, and it's more like 2 degrees, and it's very much a function of temperature. I can send out the calibration curve to whoever it was who asked that if they're interested.
That was Paul Hain. And then one more
Hey,
question: what is the field of view at the surface?
for the LCS, I want to say at 75 centimeters, it's going to be about 10 centimeters, or no, 15 centimeters. But I can get back to you on that as well. It's about 15 centimeters. And one of the requirements, accommodation requirements, is we see nothing but surface and not any of the landing blades or anything like that. So we get a clear surface temperature measurement.
Okay. And has the location on the astrobotic lander been determined yet?
Yes. We're on deck B, hanging up underneath Rick Elphick's neutron spectrometer, I believe. So if I didn't include that picture, maybe Rick's got it in his presentation. We're hanging basically right under him.
Okay, great. Well, we'll hear from Rick Elphick now, and then go back to you to hear about Viper. So
okay, I'll stop sharing.